Today I'm gonna finish the intermediate Kaggle machine learning course. And if I have time, watch some videos later, I think. Pipelines are a simple way to keep your data preprocessing and modeling code organized. Specifically, a pipeline bundles preprocessing and modeling steps, so you can use the whole bundle as if it were a single step. Many data scientists hack together models without pipelines, but pipelines have some important benefits. Those include cleaner code, accounting for data at each step of preprocessing can get messy. With a pipeline, you won't need to manually keep track of your training and validation data at each step. Fewer bugs, easier to productionize, more options for model validation. As in the previous tutorial, we work with the Melbourne housing dataset. We won't focus on the data loading step. Instead, you can imagine you are at a point where you already have the training and the validation data in X-ray and the other variables. We take a peek at the training data with the head method. Reconstruct the full pipeline in 3 steps. First, define preprocessing steps. Similar to how a pipeline bundles together preprocessing and modeling steps, we use the column transformer class to bundle together different preprocessing steps. The code below inputs missing values in numerical data and inputs missing values and applies a one-hot encoding to categorical data. So it's creating a simple inputter. But this time is using this pipeline. It just creates steps and then simplifies the process. Bundle preprocessing for numerical and categorical data. Preprocessing, column transformer. Define the model. Next, we define a random forest model with the familiar random forest regressor class. Create and evaluate the pipeline. Finally, we use the pipeline class to define a pipeline that bundles the reprocessing modeling steps. There are a few important things to notice. With the pipeline, we preprocessing the training data and fit the model in a single line of code. Contrast without a pipeline, we have to do imputation, one-hot encoding, and model training in separate steps. This becomes especially messy if you have to deal with both numerical and categorical variables. The pipeline will supply the unprocessed futures in X value to the predict command, and the pipeline automatically preprocesses the futures before generating predictions. However, without a pipeline, we have to remember to preprocess the validation data before making predictions. So, from what I understand so far, it's just a library to simplify the whole process that was done on the first part of the course, which is organizing the data to run the models. The next code cell about changes to load the training validation sets. So Just importing the creating the file and this data frames. Removing rows. Also, is removing the rows only on the column that is going to be the target. Cardinality means the number of unique values in a column. So here is doing the thing for separating the columns that have less than 10 categorical values and the numerical categories. So the first step is pretty much separating the data. Next code cell uses code from the tutorial to preprocess the data and train a model. Runs this code without changes. So creates the simple inputter, strategy constant, which I don't know what it means. Then creates the pipeline for the categorical, applying strategy. Most frequent, I think, is the strategy that substitutes the missing values with the most frequent ones, and then uses one hot encoder. Bundle preprocessing for numerical and categorical data. And I think this um, gets them together on the main data set after cleaning them up. Define the model, so pipeline. Preprocessor model, then fits and trains. Now it's our turn. In the code cell below, define your own preprocessing steps and run the first model, giving values for the following variables. Yeah, now it's the hard part. This pipeline here, true. Yeah, I don't remember. and estimators. So, so this one is just simple inputter. This one is gonna be the pipeline. Steps. Pipeline is a parenthesis, not. The other is gonna be one. I'm not sure if that's was it written there. Footer and one hot. It's most frequent. Now has these parentheses here. Now should be right. Hot encoder. When the codes are below about changes to pass this step, you need to have defined a pipeline part A that achieves lower MA and the code above. You're encouraged to take your time here and try out many different approaches to see how low you can get the MA. If your code does not pass, please amend the pre-processing steps and model in part A. So I think here I'm supposed to try different strategies, but I don't know. I know which ones exist, but I don't know how they are. I'm supposed to write them there. So let's see if this works. Mean, median, most frequent, and constant. What the hell is wrong now? Oh yeah, trying to get the mean of categorical data. Let's try 0 here. See if it works. Even though I don't remember if it's for categorical numerical data that you use the 0 strategy. So constant. Nice. There was a second argument here as well that I forgot, but I think it was matrix sparse, something like that. To make this into a vector. I think that's the second method. Second method I'm forgetting. Generate test predictions. Now you use your trained model to generate predictions with the test data. So it's the same thing they did here. The next goes solve out changes, save your results to a CSV file, and be submitted directly to the competition. So if I have to do all this by myself, instead of having their help, I don't think I know how to do everything, but I think at least I understand things a lot better now than I did before starting the course. They do a better job of explaining this pipeline stuff and all these parts than the book does that I'm reading. But the book has more information overall, so they are not complement to each other. Cross validation. Machine learning is an iterative process. You face choices about what predictive variables to use, what types of models to use, what arguments to supply to those models, etc. So far, you have made these choices in a data-driven way by measuring model quality validation, or HODL-SAT. But there are some drawbacks to this approach. To see this, imagine you have a dataset with 5,000 rows. You typically keep about 20% of the data as a validation dataset, or 1,000 rows. But this leaves some random chance in determining model scores. That is, a model might do well on one set of 1,000 rows, even if it would be inaccurate on a different 1,000 rows. At an extreme, you could imagine having only one row of data in the validation set. If you compare alternative models, which one makes the best prediction? So it's basically for outliers and stuff like that. For statistical relevance, this cross-validation method is used. Cross-validation, we run our modeling process on different subsets of the data to get multiple measures of model quality. For example, we could begin by dividing the data into 5 pieces, each 20% of the full data set. In this case, we say that we have broken the data into 5 folds. Then we run one experiment for each fold. So I guess I understand already. When should you use cross-validation? Cross-validation gives a more accurate measure of model quality, which is especially important if you're making a lot of modeling decisions. However, it can take longer to run because it estimates multiple models. So given these trade-offs, when should you use each approach? For small data sets where extra computational burden isn't a big deal, you should run cross-validation. For larger sets, a single validation set is sufficient. Your code will run faster and you may have enough data that there's little need to reuse some of it for holdout. I guess the type of data also matters because data that have more variance is probably better to cross-validate because the chances of having the validation set not represent really well the whole data set is bigger. So there's no simple threshold for what constitutes a large versus small data set. But if your model takes a couple minutes or less to run, it's probably worth switching to cross-validation. Alternatively, you can run cross-validation and see if the scores for each experiment seem close. If each experiment yields the same results, a single validation set is probably sufficient. We work with the same data as in the previous tutorial. Load the data. Then we define a pipeline that uses an inputter to fill in missing values and a random forest model to make predictions. While it's possible to do cross-validation without pipelines, it's quite difficult. Using a pipeline will make the codes remarkably straightforward. And estimator is 50. I wonder if you can, probably you can, create your own model and then use that model instead of one standard that already exists, but maybe you don't. We obtain the cross-validation scores with the cross-val score function from scikit-learn. Set the number of votes with the CV parameter. So just cross-val score. I think this is a method from the library. Yeah. My pipeline XY CV5. Cross-validation score, cross-val function. Set the number of folds with this CV parameter. So CV is the amount of times that it's gonna pick a different distribution of the test and validation. Not different in size, but different in the type, what data is gonna be on each one. The score parameter chooses a measure of model quality to report. In this case, we chose negative mean absolute error. The docs for scikit-learn shows show a list of options. It is a little surprising that we specify negative MA. Scikit-learn has a convention where all metrics are defined so a high number is better. Using negatives here allows them to be consistent with that convention. Though negative MA is almost unheard of elsewhere. We typically want a single measure of model quality to compare alternative models. So we take the average scores, average across experiments. So these are all the classifications that the library has. Clustering. I'm not gonna go through all of that now. Conclusion: using cross-validation, you use a much better measure of model quality. So at the end, there's taking the average to see roughly what's the average MA that the model got. So far, we've learned how to build pipelines with scikit-learn. For instance, the pipeline below use simple inputter to replace missing values in the data. Before using random forest regressor to train a model, random forest model to make predictions. Set the number of trees in the random forest model with the n estimators per parameter. Setting random state ensures reproducibility. So number of trees is the amount of comparisons, if I remember correctly. I think it might be interesting to investigate this concept further. What does it mean to have more or less trees? What are the implications of that? I think I'll do that later. Or maybe after reading the full book, because they might talk more about that. I'll do that later. So creates pipeline steps, preprocessor, simple inputter, model, random forest progress. I've also learned how to choose pipelines in cross-validation. Go below uses the crosswalk score function to obtain the mean error, average across 5 different folds. So just calling crosswalk from library, score -1 to make it negative, times crosswalk, my pipeline xy, cv5. Write a useful function. In this exercise, you use cross-validation to select parameters for machine learning model. Begin by writing a function getScore that reports the average over three cross-validation folds. MA of machine learning pipeline that uses data in X, Y, simple inputter, Paste this body with your code. So it's pretty much the same thing as before. I choose simple inputter and random forest regressor and CV of 5 of 3. So I forgot exactly which words were used there. I think steps equals computer. No, how was it? Preprocessor. Simple inputter. And here it was. Trying. I want you force, not force, but try to remember without looking at it, just to strengthen the memory. Here I think was model. I think model was used here. Forest regressor. And estimators equals some number, then you're gonna have random state equals 0. I think 50 here. They didn't didn't talk about how many estimators. Is used when setting the random number of trees in the random forest model. So now I think it was my pipeline equals to this. Now score and my get score. No, my score equals -1 times cross score. No, I forgot again. What was used here? So I know that I need to put CV equals 3 somewhere. I need to put XY. But I don't remember exactly. Yeah, I do not remember the structure. My pipeline. X, Y, CV equals 3. Simple before permits. I don't know where I got that is equal to 3. I'm gonna put 3 anyway. Scoring equals negative. The absolute error. And then I need to return this. Dot min, I think. Cross validation to select parameters for a machine learning model. In get score that reports the average. So needs to return the mean. No over 3 cross validation faults. I think I did correctly, but maybe the pipeline is not. I'm not supposed to write that in this function. Yeah, but no, I kinda need to because the model is defined on the pipeline. So my pipeline equals pipeline steps. I think I did this part correctly. And the first regressor. So it's saying correctly. Not sure what's wrong here. Seems like I did everything correctly. Yeah, it's the same thing. Maybe this I should have a space here. It's the only difference I see. So maybe the test is off. Yeah, I think is an issue with the test. Oh, I put equals here. That's why. So they are not expecting you to put a default for an estimators. That's a problem. Because they want to test different ones, probably. Now you will use the function. Well, come back here. Yeah, it's passed as an input, so you're gonna pass the number of estimators when you call the function. That's why it can't be equal there. Now you use the function that you define in step 1 to evaluate the model performance corresponding to 8 different values for the number of trees in the random forest. Store your results in a Python dictionary. Where results I is the average MA return to get score. You will use the function to evaluate the model performance corresponding to 8 different values, the number of trees. So I think map here. I don't remember really well how to do map. Uh, I'll have to look at it, I guess. I think it's the other way around. Maybe it's lambda. Here are the values. Oh, but no, there's multiple different ways of doing this. I don't. Probably writing all the values is not the best way. It's definitely not the best way, but so I'm using map the wrong way. Does the function first, then the thing. Let's see if this works. Python dictionary. Store results in Python dictionary results. Where uh so I have to do like this. Results I is the average MA. So I'm not sure what they mean by results I. And here is gonna be the mean of the map as well. Let's try like this. See if it works. Hmm. So probably they want me to do it in a different way. So this is gonna return the. It's gonna test. It's gonna call the function for each one of them, and it's gonna return the value of them. So maybe meaning has to be inside of this. Well, but then it doesn't work. Shouldn't the output be the list with the values? Mm. So what they want is a dictionary with the main being the first one, and the other parameters being the average, being the score. I don't understand. I'm gonna look at the hint first. I think I know how to do this, but it's just gonna take a lot of work. It's pretty much finding the way to put them all in the dictionary and stuff like that. But by instantiating the dictionary of results equals this, then loop over the value for an estimators that will be plugged into the get score function and use the result to set the value in the dictionary. Yeah, so I know how to do this, but I don't feel like doing it right now. So just gonna copy the solution, move on. I don't understand why 50 times y though. 50 times I. Oh, I get it. It's because each one has to be 50 apart from each other. So the I is gonna determine how many trees there exist. And I wasn't thinking about doing like this. I was thinking about doing the append stuff. So this is my practical. But yeah, definitely know how to do that in a bunch of different ways, probably. Now it's just visualizing the result. And we see that 200 estimators is the best. Worst actually, because the higher the score, the better, I think, since it's negative. Find the best parameter value. Given the results, which value for an estimator seems best for the random forest model? Oh, there's no way to see here. Oh no, wait, it's 100. No, so it is 200. It's not 100. I thought I read that since they're using negative estimators, the higher the better because it means lower if it's negative, obviously. But apparently that's not the case. If you'd like to learn more about hyperparameter optimization, you're encouraged to start with grid search, which is a straightforward method for determining the best combination of parameters for a machine learning model. So you could learn us grid search. I've seen this in one of the solutions before. Still have 1 hour, almost more than 1 hour. I think it's gonna be enough to finish everything. Maybe we'll write here. Um, and estimators. For much of this course, you have made predictions with the random forest method, which achieves better performance than a single decision tree simply by averaging the predictions of many decision trees. We refer to the random forest method as an estimator and an ensemble method. By definition, ensemble methods combine the predictions of several models, several trees in the case of random forest. Next, we will learn about another ensemble method called gradient boosting. Gradient boosting is a method that goes through cycles to iteratively add models into an ensemble. I think I already get it just by the name. Begins by initializing the ensemble with a single model whose prediction can be pretty naive. Even the predictions are wildly inaccurate, subsequent additions to the ensemble will address those errors. It's basically an iterative process to find the global minimum instead of the local minimums. That's my guess. Start the cycle. First, we use the current ensemble to generate predictions for each observation in the dataset. To make a prediction, we add the predictions from all models in the ensemble. These predictions are used to calculate the loss function, mean squared error, for instance. Then we use the loss function to fit a new model that will be added to the ensemble. Specifically, we determine model parameters so that adding this new model to the ensemble will reduce the loss. The gradient boosting refers to the fact that we will use gradient descent on the loss function to determine the parameter in this new model. Finally, we add the new model to assemble and repeat. So naive model make predictions, calculate loss, train new model, add new model to assemble. So it's basically the I understood this. I thought it would be about finding different steps to find a global minimum, but it's just the first, because until now, so far, we haven't used gradient descent to readjust the predictions. So I guess XG boost is just the gradient descent part, where the prediction becomes the loss function. Is embedded, inputted on the loss function, and then the model trains again based on the gradient descent thing. We begin by loading the training and validation data in these things. In this example, you work with the XGBoost library. XGBoost stands for Extreme Gradient Boosting, which is an implementation of gradient boosting with several additional features focused on performance and speed. Scikit-learn has another version of gradient boosting, but XGBoost has some technical advantages. Next code cell, we import the scikit-learn API for XGBoost. This allows us to build and fit a model just as we would in scikit-learn. As you see in the output, the XGB requester class has many tunable parameters. So it just creates the model here and then fits. We also make predictions and evaluate the model. Parameter tuning. XGBoost has a few parameters that can dramatically affect accuracy and training speed. First parameters you should understand are N estimators. N estimators specify how many times to go through the modeling cycle described above. It is equal to the number of models that we include in the assemble. Too low a value causes underfitting, which leads to inaccurate predictions. Too high causes overfitting. Typical values range from 100 to 1000. Though this depends a lot on the learning rate parameter discussed below. So now I was going to talk about this step, which is how much the backpropagation is going to adjust each iteration. Adjust the next prediction until it reaches global minimum or local minimum. Early stopping rounds offers a way to automatically find the ideal value for N estimators. Early stopping causes the model to stop iterating when the validation score stops improving, even if we aren't at the hard stop for N estimators. It's smart to set a high value for N estimators and they use early stopping rounds to find the optimal time to stop iterating. Since random chance sometimes causes a single round where validation scores don't improve, you need to specify a number for how many rounds of straight iteration to allow for stopping. Setting earlier stopping rounds 5 is a reasonable choice. In this case, we stop after 5 straight rounds of deteriorating validation scores. When using early stopping rounds, you also need to set aside some data for calculating the validation scores. This is done by setting the eval set parameter. You can modify the example above to include the early stopping. If you later want to fit a model with all your data, set n estimator to whatever value you want to be optimal when run with early stopping. The learning rate is just this step. Larger data sets per runtime is a consideration. You can use parallelism to build your model faster. It's common to set the parameter n jobs equal to the number of cores on your machine. N jobs. And so here. The resulting model won't be any better, so macro optimizing for fitting time is typically nothing but a distraction. But it's useful in large data sets where you would otherwise spend a long time waiting during the fit command. So essentially, early stopping is for when the error decreases, but then it starts increasing again because of overfeeding. And then this is how many rounds uh, it stops before it reaches the number of trees you put through it, I guess, from what I understand so far. So it's doing all the basic steps, dropping values from sale price that don't exist, separating the data sets, selecting columns that have uh, up to 10 unique values with this loop, and selecting numerical columns, then joining them together. On how to encode the data, they get dummies, string get dummies. Oh, I didn't know you can do that with pandas. Part A. In this step, you'll build and train your first model with gradient boosting. Begin by setting my model 1 to an XGB boost model. Use the XGB regressor class and set the random seed to 0, with all other parameters as default. Then fit the model to the training data in XY. I don't remember if there's more than one argument there. Probably forgetting something here. Oh, it's correct. I'm gonna look at the solution just in case, just see. Yeah, so it's just random state. Set predictions 1 to the model's prediction for the validation data. Recall that the validation features are stored in X value. So predictions, you're gonna call my model and predict. My model 1 dot predict X value. Correct? And then you're gonna compare I forgot the a noise against the y. I'm gonna get this variable and y valid, but oh, mean absolute error. Then y valid and predictions 1. Correct. Prove the model. Now that you've trained a model, but default model as baseline, it's time to tinker with the parameters to see if you can get better performance. Begin by setting model 2 to an XGB model using the XGB regressor class. Use what you learned in the previous tutorial to figure out how to change the default parameters, like N estimators and learning rate, to get better results. Then fit the model to the training data in XTrain and YTrain. Set predictions true to the models. It's pretty much the same thing as above. But I forgot this stuff that I'm supposed to do here. I know what I need to do, but I forgot how it's done. No, it's random state, not estimators. And I know there's a snap and jobs, which is should be equal to the number of cores in the computer. And I think there was another thing here that I need to do that I forgot. The rest is pretty much the same, I guess. X string, Y, right? Then my model dot predict X valid mean absolute error equals Y valid and prediction is true. I'm gonna test to see if it passes, but actually regressor is not defined. Maybe it's a typo. Yeah, put XBG instead of XGB. My model shoe is not defined, so it's my model instead. Let's see now. Incorrect. You must specify the parameters in my model 2 so that it trains lower MA than the model 1. Parameters step might not be used. So it not supposed to use step here. Let me see on the tutorial. Learning rate. Does not steps learning rate. Let's put 0. I'm probably forgetting more things. No, correct. Okay. So I got confused with the pipeline stuff. I keep thinking, for some reason, I think I'm forgetting. I think it's because of the gradient descent stuff. It feels like I'm missing something. In this step, you create a model that performs worse than the original model in step 1. This will help you to develop your orientation for how to set parameters. Might even find you accidentally get better performance, which is ultimately a nice problem to have and a valuable learning experience. Begin by setting my model tree to an XGB model using the class. Use what you learned in the previous tutorial to figure out how to change the default parameters like estimators and learning rate to design a model to get high MA. So I'm gonna use a really big learning rate because I want to get a bad score and small estimators, I guess. And the other one I used and jobs as well. Not gonna use that here. I'm not sure if if small estimators makes a better. I think it's in the middle is probably gonna give the best results. So depending on the data set, the scale of the models become different. But my best guess intuition says that usually it's gonna be the middle. But the middle is gonna change depending on what type of data it is. And how much of data you have. So a really small number and a really big number are probably bad, but that depends on the scale of the data. So I think putting a small is probably gonna give me a high MA on average. Fit the model. My model 3, not fit. Get predictions. Predict. That's valid. The good thing is that I'm remembering these steps now. I think I already got down on my head that for making predictions you use the X validation and not the Y. That's the other way around. Mean absolute error. Correct. Nice. Let's see the solution. Uh, an estimator is one. Yeah. They didn't put the number of steps, but they put a low n estimator. So I guess my intuition is correct. Maybe. It's still 47 minutes. I think it's plenty of time to finish. There's only one more tutorial, I think. I'm gonna go to the bathroom, be right back. So let me see what time it is. Data leakage or leakage happens when your training data contains information about the target. But similar data will not be available when the model is used for prediction. This leads to high performance on training data and low on the validation. There are two main types of leakage: target leakage and train test contamination. Target leakage occurs when your predictors include data that will not be available at the time you make predictions, It is important to think about target leakage in terms of the timing or chronological order that data becomes available, not merely whether a future helps make good predictions. An example will be helpful. Imagine you want to predict who will get sick with pneumonia. A few rows of your raw data look like this. People take antibiotic medicines after getting pneumonia in order to recover. The raw data shows a strong relationship between those columns, but took antibiotic medicines frequently changed after the value forgot pneumonia is determined. This is target leakage. So, yeah, basically the value is going to change based on the other one. The model would see that anyone who has a value of false for took antibiotic medicine didn't have pneumonia. Since validation data comes from the same sources as the training data, the pattern will repeat itself in validation. The model will have a great validation or cross-validation scores. But the model will be very inaccurate when subsequently deployed in the real world, because even patients who will get pneumonia won't have received antibiotics yet when we need to make predictions about their future health. To prevent this type of data leakage, any variable with data created after the target values realized should be excluded. Train test contamination. A different type of leak occurs when you aren't careful to distinguish training data from validation data. Recall that that validation is meant to be a measure of how the model does on the data that it hasn't considered before. You can corrupt this process several ways if the validation data affects the preprocessing behavior. This is sometimes called train test contamination. For example, imagine you run preprocessing like feeding an inputter for missing values before calling train test split. The end result, your model may get good validation scores, giving you great confidence in it, but perform poorly when it deployed to make decisions. After all, you incorporated data from the validation or test data into how you make predictions. So they may do well on that particular data, even if it can generalize to new data. So this one I don't completely understand. Feeding an inputter. Guess I forgot a little bit how the inputter works. Oh, it's inputting missing values. Replacing missing values. Before calling train test split. But I don't understand necessarily why that would be bad before splitting the data. Oh, I guess it's because when you're training, you want to get good predictions, but on the test, you're gonna have to use data that doesn't have the stuff that you use to train. And part of the training is trying to figure out what's the best way to optimize for this incomplete data and the real world case. So just because you're training when with no missing values doesn't mean that you don't want to achieve high scores for missing values as well, for data with missing values, because that's the point of training. If your validation is based on a simple train test split, exclude the validation from data from any type of feeding, including the feeding of preprocessing steps. It's easier if you use scikit-learn pipelines. When using cross-validation, it is even more critical that you do a reprocessing inside the pipeline. Example: in this example, we learn one way to detect and remove target leakage. We will use a data set about credit card applications and skip the basic data setup code. The end result is that information about each credit card application is stored in the data frame X. We use it to predict which applications were accepted in a series Y. Since this is a small data set, we use cross-validation to ensure accurate measures of model quality. So creating the pipeline. Since there is no pre-processing, we don't need a pipeline. Use anyway as best practice. Then cross-validation. With experience, you'll find that it's very rare to find models that are accurate 98% of the time. It happens, but it's uncommon enough that we should inspect the data more closely for target leakage. Here's a summary of the data, which you can also find under the data tab. 1 if credit card application accepted, 0 if not. Age, income, share, expenditure, owner. A few variables look suspicious. For example, does expenditure mean expenditure on this card or on cards used before applying? At this point, basic data comparisons can be very helpful. Card holder, expenditure. As shown above, everyone who did not receive a card had no expenditures. Only 2% of those who received a card had no expenditures. It's not surprising that our model appeared to have a high accuracy, but this also seems to be a case of the target leakage, where expenditures probably means expenditures on the card they applied for. Since share is partially determined by expenditure, it should be excluded too. The variables active and major cards are a little less clear, but from the description they sound concerning. In most situations, it's better to be safe than sorry if you can't track down the people who created the data to find out more. We would run the model without target leakage as follows. So one thing that comes to mind is, why not build a script that tests a bunch of relationships? Maybe it's because the computation takes too much time, but I think that would be the most efficient way of automating this process, instead of spending a bunch of time thinking about which one is better, in which sets should be dropped or not. You can create a loop that takes just a portion of each set, kind of like in cross validation, but not for splitting the test and validation, but for finding which columns have the best correlation between them and make the best prediction models. This accuracy is quite a bit lower, which might be disappointing. However, you can expect to be right about 80% of the time based on new applications, where the leak model will likely do much worse. The data leakage can be a multi-million-dollar mistake in many data science applications. Careful separation of training and validation data can prevent trained test contamination. And pipelines can help implement this separation. Likewise, a combination of caution, common sense, and data exploration can help identify target leakage. Turn off the shoelaces. You have any idea? Use them on the leather neck or the. This is not interesting to me because I understand the concepts already. It's more of I guess the exercises are gonna be more about each data specifically, but I understand already the underlying principles. So that is not so much about a new library or methods, from what I understand so far. Just about understanding what data you're working on and finding intuitively which ones are better to draw. Yeah, I don't think it's gonna have any exercises that I need to write stuff down. Just this one, but it's probably based, yeah, it is based on the data set, which I'm not gonna do. Maybe I should try to guess here randomly, see if I get it right. Size of the house, average sales price, to the longitude of the house, whether the house has a basement. I think it's three. Let's see. It's correct. So maybe four. One. Damn, it's the last one. Yeah, whatever. Yeah, so I guess this is it. Categorical. It's probably something here I didn't do. They didn't run. The notebook didn't run, but pretty sure I did everything. Let's see now. What's up with this? Maybe it's this one? Oh, it's zero there. Not 100. Nice. How many entries are added to the dataset by replacing the column with ordinal encoding? No, it's because it's a different type of encoding. Yeah, it's done. So I'm done for now. I think I might come back today later to watch some videos and study some stuff. But yeah, see ya.